Hello, my name is Sierra, and I'm here with Devin and Kyle. We're all chemical engineers. For our senior design project, we did the large scale steam decontamination system. Our project number is 19135. And so this is our poster. Given the circumstances, we would have presented this on design day, just like this. However, since we are doing a virtual design day, we're just going to show you what our poster would look like, and then I'm going to go ahead and go through a power presentation to demonstrate it a little bit more. That way it's a little bit more clear and not just everything in your face. Okay, so with that being said, we'll go ahead and start the presentation. So first I'm going to get into a little bit of background, some project description and goals, and then a company background, then a PFD, some assumptions, calculations, conclusions, and then finally our references. So first, a little bit of background. What is steam decontamination? Basically, it's where you expose an item to steam for a specific amount of time to remove microorganisms, mold, or chemicals. And we want to do steam decontamination because it's non-toxic, it's inexpensive. There are 4 parameters that are needed to be taken accounted for, which is steam, which is going to be saturated, pressure, temperature, and time. So a little bit more background. What are we specifically contaminating, which is this plant called Costus igneus, which is an insulin plant. This plant is important because it's an herbal cure for diabetes. The leaf length is 4 to 8 inches. The leaf width is 2 to 4 inches. This will be important later down the road when we do our calculations. So some typical contaminants that we are trying to get rid of are pesticides, bacteria, yeast, mold, and various metals that are in the soil when the plant is growing. So first, what is our project description? Currently, UrbanX Labs uses a small-scale steam decontamination system instead of gamma irradiation. And our goal from UrbanX is to optimize their current process. So they had a few constraints that we had to follow, which were we had to scale up their current design by 10 times the current capacity. Their current design allowed for a 5-minute steam decontamination chamber, and they wanted to knock that down to 1 minute. And lastly, they had a couple things in their current design that they no longer use and would like to take it out, which is the vacuum drying and the mixer that they don't want anymore.
A little bit about UrbanX Labs. They are a company based in the Philippines that focuses on processing medicinal plants in order to move from industrial medicine, which we have kind of here out west, to more traditional used powder herbs and extracts and teas and things. I guess some reasons that they would want to do this include it's very inexpensive and widely available considering they can grow it themselves in their own country and with no middleman to worry about going from planting and growing to harvesting and decontaminating. There's far less side effects from these natural plants. A little bit about our process flow diagram here. In the first heat exchanger on the left is our decontamination chamber, where it goes through, it gets decontaminated. And then in the second one, we condense the solvent that is used, which we then store in the tank T101, sort of middle right here, which can then be directed either via pump P101 or valve V101, depending on where it is needed in their plant. Some assumptions we did make during this process, given the lack of information, was that steam decontamination of our herb is similar to the pasteurization of beef. They have to meet similar regulations as far as food and handling go. It gives us an idea of some numeric purity that we can evaluate as well. A leaf thickness of 2 millimeters was something we also assumed, which aided in our calculation. Given that the plant is very much composed of water, our density that we assumed was that of water. And finally, our solvent that we recover remains in the tank for up to a month. The most important initial calculation in this process was calculating the steam flow rate needed in the steam decontamination chamber. To do so, we had a saturated steam at a temperature of 132 degrees C. And in order to sterilize at that temperature, you have to have an exposure time of 2 minutes. Then, using the density of our herb and the mass that we are required to decontaminate, we found a volume of the chamber of 250 liters, and we were given by our mentor a pressure of 3 bar with which to decontaminate at. This yields a total flow, I guess, of a little over 22 moles of steam, and then applied over the 2-minute exposure time is a little over 12 kilograms an hour.
All right, now I'm going to get into how we calculated some of our costing. We started with the new equipment, and we used the new desired herb flow rate and the new calculated steam flow rate to determine different equipment sizes, depending if it had herb going through it or steam. We then went into the utilities and raw material costs, the utilities being electricity and the steam. The raw material is, of course, our raw costus igneus, the insulin plant. We then went into various costs of manufacturing. We then determined an appropriate selling price so we can determine what kind of revenue the system can make. And then using these different pieces of information, we determined the economic feasibility of the system by doing a cash flow analysis. All right, so in the end, we found that the system has high upfront costs, around $27 million for purchasing the equipment, about 2 months of raw materials that you will need to put into the system before you get any kind of revenue. The system also has high annual costs, around $4 million a year, due to the utilities, the steam, electricity, as well as the raw material cost. However, these high costs are offset by the system's very high revenue, which is around $77 million per year, which is much higher than the upfront costs and annual costs. So after taking into account inflation and depreciation of equipment, this system is projected to be very profitable. It's projected to be profitable at nearly any reasonable rate of return. Just to give you an idea, after 1 year of operation, all investment costs are recovered at a discount rate of 33%, which is very high. So looking at a pretty standard discount rate of 15%, the system produces over $262 million of profit over 10 years of operation. So since these profit margins are incredibly high, it makes this system a great investment. These are the references we use for our various calculations. And thank you for your time.